Hello, everyone who's joined so far. I think we might wait a moment or two just to make sure people have figured out the technology. I wanted to confirm that our captioner was all hooked up, and I see it's already working, so that's great. If you would like that, somewhere near the bottom of the screen, there should probably be a CC button. It might be hidden in the 3 dots more menu, and you'll get subtitles of what people are saying in case you have hard hearing or hard time with English or people's accents. Hopefully this will help. As I said, I'll wait a couple more minutes and then we'll actually get started. Okay, shall we begin for real? So, welcome all. Thank you for joining us, especially if this is an awkward time of day for you. My name is Amelia Bellamy-Royds. I'm one of the members of the programming committee who has been organizing this workshop. So welcome to what you are participating in is the W3C OGC, get this title correctly, W3C OGC workshop on maps for the web. So our host organizations, the W3C, the World Wide Web Consortium, works on standards for the web platform. The OGC, the Open Geospatial Consortium, works on standards for geospatial data and mapping. And our more specific hosts, the Maps for HTML community group, which is a open to pretty much everyone group of people interested in getting a map presentation on the web more standardized. And our host / sponsor is Natural Resources Canada, who have been funding a lot of this work and who are paying for the captioning and a few other logistics related to the workshop. So speaking of logistics, if you are here in person, then you have successfully joined the Zoom conference. Glad you made it here. If you are watching a archived video because you weren't able to join the Zoom conference, for reasons due to troublemakers jumping on Zoom calls, we're not posting the live Zoom links on the web, but if you registered for the conference in advance, you should have gotten an email from Ted Guild that says something about workshop logistics in the title, and it will have the Zoom link. If you are registered and you can't find that email, then do try to reach out to the programming committee members. There are email addresses on the website, and we will try and get you connected up for the rest of the workshop. Related to that, if you can't participate in the live sessions, they are going to be all different times of the day, and we know they aren't convenient for everyone. We will be recording all the sessions and trying to post them online within a day or two so you can catch up by watching the recording. And the recordings will be hosted on the W3C YouTube channel. The discussion will continue on the WICG discourse server. And we'll have kind of open forum on each topic where people can add comments, add more examples, really go in more depth than we can on a video conference situation. There is also a live chat on Gitter that we've set up. So that's just more casual conversation as we go along. It's where we'll be sharing links and such as we go. And just during the course of the workshop, it's a way to ask questions of other participants or any logistical issues that come up. And if you're not familiar with Gitter, it's just a chat application, single column chat room. You can log in with a GitHub account, with a Twitter account. I think you might be able to make an account directly on the site, but hopefully most participants have at least one of those ways to log in. And finally, a note, there is a chat built into the Zoom interface. We're going to try and keep that to Zoom specific comments. If there are technical difficulties, if you can't hear someone, if you can't see their screen share, you can put it in the Zoom chat. But the Gitter and discourse will be kind of the more lasting chat that persist even after we close down the teleconference. One final important thing to mention, this is a professional event. We are operating under the W3C's Code of Conduct. We expect respectful treatment of everyone. If you have any concerns about that, if you want to read the full code of conduct, it is linked from the website. Somebody could even put a link into the chat so we can show that the chat works. And if you do have any concerns about any of the content, any of the behavior of other participants, you can reach out to the programming committee members or the W3C Ombuds office. And I think that was all my logistics and introduction. Only took 10 minutes. So with that all out of the way, I'd like to introduce our first speaker of the workshop. Peter Rushforth is a geologist and GIS expert who now works at Natural Resources Canada with a specific focus on standardization for geospatial information and maps. And he's been one of the most persistent driving forces behind the Maps for HTML project. He's going to be talking to us today kind of as a big introduction to the whole purpose of the workshop, why maps for the web are worth talking about, are worth standardizing, are worth getting excited about. Okay, Peter, you ready to go?
Good evening and good morning. My name is Peter Rushforth and I work for Natural Resources Canada's Centre for Mapping and Earth Observation in the Canadian Geospatial Data Infrastructure Division. Today I want to talk about why we need to standardize maps for the web in HTML. There are many reasons that people need or want to make web maps. In the domain in which I work, it's a requirement of most projects. But how do you make a web map? It's easy, right? There are lots of ways to make a web map. You just need to pick a framework. Each framework has its merits. Some are easy to get started with. Some come with a bunch of free data layers built right in. Others require significant knowledge and/or manipulation of data and access to computing resources. Accessibility is not guaranteed, and it's easy to mess it up. Interoperability pretty much does not exist. In short, there is no simplest choice, and it can be a big decision. Once you decide, all the code that you write does belong to you, except it's bound to the framework you've chosen, making any change expensive and painful. The result? The result is silos. Although each web mapping framework is somewhat similar, none share the same foundation and they are not interoperable except in that the user can see a map. The result is bad for users and the web. Why do silos exist? Silos might be caused by proprietary interests, such as those created to lock users into software platforms. But more likely they exist because we didn't take the trouble to collaborate and eliminate the barriers or to create interoperability. The proposal we'd like to make in this workshop is, why don't we work together to support all the users? Mapping framework providers are all trying to serve their users. Collectively, the sum of their users is approximately equivalent to humanity as a whole. All the map providers use the web as their medium of choice to deliver their products. Together, let's improve the web to serve all of the providers equally well, possibly reducing their individual frameworks' responsibilities. Let's make a standard that helps with the common core that these providers can progressively enhance if need be. Let's make a standard to serve users' needs directly through common accessibility, privacy, safety, linguistic, and usability infrastructure, just as we try to do for users in the real world with roads, bridges, sidewalks, crosswalks, signs, etc. While we're at it, let's make the standard a natural first step in learning so that maps can be taught at school, giving children a common starting point for learning about geography and the web without frameworks. Can silos truly disappear, though? The test of independent invention, first described by Tim Berners-Lee, is a kind of thought experiment. The notion is that any new protocol or format must be designed for introduction into an environment that has incumbents, or it cannot succeed. At the invention of the web, for example, FTP, Gopher, WACE all existed in the mainstream already. HTTP, HTML, and URLs were designed to work with the existing protocols, somewhat satisfying the test of independent invention, which can never be perfectly resolved. You can't make silos disappear, but over time they can resolve on their own. In the real world, infrastructure often describes public facilities created for the benefit of all without prejudice. Such infrastructure must be safe and accessible, safe for everyone to use. It must be fair and inclusive. What good would roads and bridges be if you could only drive a Ford on them? It must be durable, because everybody uses it. Infrastructure must be built to serve and last. And finally, it must be cost effective. Infrastructure should make it less costly for everyone to achieve their goals. Note that this does not mean that it's free. In fact, it can be quite costly, but it should be maximally shareable. In the virtual world, the World Wide Web and the software that supports it is virtual but nonetheless real infrastructure. But how do we avoid creating more silos in standardizing maps and spatial data for the web? The situation in web mapping standards is a little bit like this XKCD comic. There are probably more than 14 different ways to create a web map, and trying to make the situation better by adding another framework risks creating a worse situation. So what to do? Can we fix the situation by adding another standard? Probably not. Many existing formats for geospatial information already exist. If one of them was suitable, it probably would be a web standard. The challenge is to create a new format that enables web maps without requiring web browsers to radically change or change their architecture, which is impossible. Proposed solution is to add and extend mapping elements in HTML. HTML is widespread, and it's the foundation of web architecture, and browsers are based on processing it. The bonus is that HTML already implements basic map semantics. HTML, pictured here, is the core language of the web, and it was designed to bridge the divide between programmers and users. Ideally, it allows everyone to have access to content regardless of ability. Further, it is straightforward enough to allow users to become authors. This is embodied in the idea of view source culture, in which the medium itself teaches the user what is possible and how to achieve it. Why are maps in HTML preferred over maps in JavaScript in the future? Because HTML requires and delivers interoperability, the browser will become a spatial integration platform. Shared standardized semantics mean interoperability. Discovery. Because of the rule of least power, web pages could have location. Indexing pages by location, search engines will become spatial discovery platforms. HTML requires and delivers inclusivity, understandable and creatable by authors who are not necessarily programmers, or authors who are not necessarily mappers for that matter. HTML requires and delivers accessibility. Because things, not just web pages, have location, the browser will tell the user about their physical environment as described by a web map or website. For public spaces, real infrastructure will be represented also as virtual infrastructure. HTML requires and delivers performance. Less runtime costs to HTML than to JavaScript mean map rendering is better and more suitable for native code. HTML requires and delivers scalability related to performance and inclusivity, and possibly other aspects of this list. Scalability means maps will work in constrained or powerful environments. HTML is like the standard library of the web. A single element encapsulates processing steps, especially rendering, from the layers below. Maps and location belong in the web's standard library so that sophisticated applications can be built on top of the web without having to reinvent the wheel. HTML is simple enough for a web crawler to understand, but scales to underlie very sophisticated application development. Even though modern web crawlers can execute web applications to reveal the application-generated HTML and text content, they can't understand semantics that aren't there, such as maps and location, which don't exist yet in HTML. Standardized location is important not only for search and discovery, but also for accessibility and internationalization. A key aspect of HTML is that it is standard. Its elements have defined visual and accessibility semantics, making it inherently inclusive. Adding maps to HTML could aid important use cases for users, such as search and discovery, reducing the need for special purpose catalogs, and the same linkability or web superpower that allows crawlers to enable search and discovery will also enable map service federation and location information sharing. HTML is inherently cross-platform, making it the ideal target for standardizing location information. These aspects taken together mean that maps in HTML will be more economically effective than our current silos, leading to better return on investments for society. HTML was a massive decade-long effort, and there's little appetite in the web standards community to repeat such an effort. HTML does, however, constantly change, and today the HTML standard itself is evergreen, with new ideas being integrated and browsers implementing constantly. So how does the process work? Ideally, developers like us who use JavaScript, HTML, and CSS provide feedback to the web platform engineers who prioritize implementing low-level features that are of use to the largest number of people. Often, these features are of JavaScript, but also of CSS and HTML. As low-level features are implemented, the thinking goes, developers will develop high-level features as libraries or custom elements. As the high-level functionality that becomes widely used, it thus becomes an emergent or de facto standard. These de facto standards can then be implemented natively by browser developers, giving rise to wider and improved use of the web and consequent generation of new requirements from new communities like our own, participating in the virtuous cycle, and so on. That maps are an emergent characteristic of the web, even constituting a GeoWeb, is obvious to the most casual observer. Maps in the HTML of the future might look like this, starting with a map element containing one or more child layer elements. There already exists a somewhat neglected map element in HTML with similar enough semantics to provide a good extension point, in keeping with the HTML design principles. By specifying a new child layer element, HTML could immediately incorporate dynamic web map semantics as commonly understood, providing the shareable infrastructure that web maps and geospatial information require. HTML has evolved over time. It began as simple text documents linked together. It was the linking that made them special. Linking has been described as the web's superpower. Over time, media types have been added in response to user needs, and most recently with the advent of the mobile web and responsive design. Maps should be the next big thing. So, where actually is this virtuous feedback loop of which I spoke? The Maps for HTML community group was created based on the conviction that web mapping is an emergent or de facto standard of the web, as sought by the Extensible Web Manifesto. The main way to provide feedback to the browser standards community is for you, especially representing your organization or company, to join the Maps for HTML community group to contribute ideas, comments, and even code. Another important path for feedback from web mapping community to the web platform folks is the annual Mozilla Web Developer Needs Assessment, or Web DNA survey. Please share the link. Mention web mapping. Mention maps in HTML. A key feature of the URL-driven web of HTML is the ability to share documents using their URL. This feature of the web also enables linking within and between resources, not to mention search and discovery. The simple architectural characteristic could make a GeoWeb of the future a benefit to users around the globe and to the interests that rely on it. In other words, everyone. HTML will provide a common foundation for maps and location for all stakeholders. Spatial information is infrastructure, and a standard that represents its common foundation will unlock the true value of that infrastructure. Maps, standardized in HTML, will allow us to encode and share our understanding of the world. Let's achieve the understanding of our physical world by enabling the representation of that world in HTML together. Thank you.
Hello. I'm done. Is that?
Okay, thank you, Peter.
That was great. Thank you. Thank you.
Okay, I think in future we'll probably have breaks between themes, but since today is a short day, I might just jump right ahead. So, our next talk of the day is by Amelia Bellamy-Royds. That's me. So, before I got distracted into organizing a workshop, my first task working with the Maps for HTML community group was to really assess the project that Peter and others in the geospatial community had done and focus on ways it can move forward within the web standards world. I've been working within web standards for a few years now, primarily SVG, vector graphics, CSS, also accessibility as it relates to those two topics. And found the potential of web standards and also some of the limitations. We can't just add everything and anything to the web because the web platform is implemented in multiple environments that need to run on all sorts of devices, and it's not unlimited what these devices can do. We can't just keep adding code, and whatever we do add pretty much has to stick indefinitely, or at least that's the goal of web standardization, that once we have websites that are out there and that work, web browsers try to support those going forward as much as possible. So there's a lot of caution in the web standards world about adding new features to make sure that those features are the right ones and are designed correctly. So one of the most important mental frameworks that is currently adopted by web standards folks is this idea of an extensible web, that the best thing the web platform can do is to create tools from which website authors and web application developers can build the features they want and test them out and get the right shape of the features as the website authors like them and as website users like them, with the end goal, at least in theory, that by demonstrating that there is a demand for a certain feature and a certain design, then they can bring that to the web standardization process and say, this is a tested idea, this is a proven design pattern, there is clear demand for it, let's get it in standards. So when I'm coming from with the Maps for HTML project, my first task was to look at what maps are already on the web. And there are maps on the web. There have been maps on the web since the very beginning well, almost the beginning. Ever since there's been images on the web, there have been maps on the web. There have been pictures of maps, the same way in a printed textbook, you have a picture of a map. And shortly after that, there was the first interactive maps using the map element that Peter mentioned briefly. The map element as it currently exists in HTML isn't specifically about geographic maps, but it can be used for it. And you'll see on my screen, I have a image map that is on one of the websites I use every day, the weather forecast in Canada. And it's just a simple picture that they generate on their web server of a map of Canada with icons and text baked in. But then there are different links to different forecasts, and you can click through and find out that here where I am in Edmonton, it's currently 14 degrees Celsius on a Sunday evening. Now, this has nice features. It's supported widely in most browsers. It's even accessible to keyboard, although I discovered when I was playing with it earlier that it's no longer fully accessible in Chrome because I'm tabbing through these links in the picture and you can't tell where I'm tabbing. So even browsers break accessibility now and then, and that's not a great thing, but the good thing about it is once they fix this bug, every image map will get fixed on the browser because the browser actually knows what it's looking at. It knows that these are links. It knows that the links have a certain shape. And so there is some semantic information there. But this is really all the browser knows about a map, is a picture with certain regions of that picture having links on them. That isn't the map as we think about web maps today. So the current conception of a web map probably looks something more like this. Here's a Google Maps embed, and it's zoomed in to Edmonton, but I can zoom out so you can see all of North America. I can pan over to Europe. I can do lots of things, and I could also have links on this, but it's interactive. It's not just a single image, it's a complex data model behind what the map is. So this is really the very simplest modern conception of a web map is something that we can work with, and the user can find the information that they need within it. So from that, we go into this idea of what are the use cases and requirements for our web maps. If we actually define what are those features that make what we now consider to be a web map. And because I'm working from this extensible web model of looking at what website developers and users have already come to expect, the approach taken for this report, which is still incomplete draft, and we welcome your contributions, is we're going to be looking at existing implementations of web maps and what are the common features that they have, what are the use cases they serve, and also what are the limitations. Because of course, if the existing web maps solve all the use cases, then we don't need to change anything. We don't need any new standards. But there are limitations that come from the fact that these maps are being rendered using a lot of code that needs to be downloaded in every website, and the final representation doesn't have a semantic meaning that the browser can understand and build on and adapt. So the specific examples we're looking at, and we can maybe add more of these, but they get a lot. So we're looking at two types. The sort of more declarative approach that's currently available on the web are anybody can go to one of these major mapping services, create a map in the user interface, the visual user interface that looks good, and get an embed code, which they can copy somewhere else. So that's the easy to use for a website author, content creator who might not be an expert in web mapping. Excuse me. And then the other type of web maps we're looking at are the JavaScript frameworks, which require a little more expertise for the website author to code them up and run the code on their site that builds the map dynamically. But they're a lot more flexible for website developers who want to add their own features or their own content. So this page is one of the many pages of examples we're building for the report, just so we can look at how these different existing tools implement the features. So this is the very minimum basic map that comes up. What do you get when you just say, put a map on this web page? In some cases, it's very plain, no labels. Other have a more content in the initial. And for the scripted ones, we've got the examples of how much code you need to include in order to get that map on your web page, which of course goes to the accessibility for website authors. And that gets me to a question. When we're talking about use cases, it's worth thinking about use cases for whom. Who are we thinking of using these web mapping tools? So within the report, we're looking at three main groups, or I guess, yeah, three main groups. The content author who's creating a website or creating content for a website or a blog or something on the web, and they just want to add a map to their blog post, to their article, to their web store. They're not geospatial experts. They're not necessarily programming experts. They want the map for the content it presents. And so what type of content? What are the basic types of maps? Simple point on a map for this is where my restaurant is located. This is where my store is located. More complex data or more complex imagery, it builds up depending on what it is. So some of the slightly more complex examples we're looking at are have a pop-up next to the marker. So there's a marker on the map, but you want extra information, a little bit of HTML. So we've got an example of the different ways you can do that in different libraries and the amount of code that it takes to do that. So Leaflet has a very built-in method of how to create a pop-up, and you get a lot out of the box from a couple lines of authoring code, and you get event handling for opening and closing, and it positions, and you can zoom out and it still works. So there's a lot of behavior there. Other libraries takes a little more manual code to get the same behavior. That's the open layers code for the demo. And so the website author, to get this particular same behavior of a pop-up from a marker point, needs a little more work. So those are the kinds of things we're looking at, use cases, not only what you're doing, but how much work it takes as far as writing code to make that happen. Some other quick examples of content author use cases, highlighting a region rather than just a marker point. So for this example, we're using GeoJSON as the data format for describing that polygon, and how easy is it to get that custom GeoJSON shape into our map so that it lines up and can be styled custom. Sorry, I've got Zoom popping up and blocking my browser screen. Go over there. Okay. Then another use case is actually not mapping at all. This is not a map, it's a painting, but it's a painting rendered within the mapping applications. This is Leaflet.js, not with OpenStreetMap tiles, but the reason you might want to have a painting in a mapping application is so that you can use the tiling with zoom effect, where as you zoom in, you load additional images with higher resolution instead of loading a giant file at the beginning. So this is an important aspect that we're considering within our use cases report, is how can the mapping tools and the features that are necessary for a good web maps, how can they also be used for other things that people want to do within the web platform? And if we can find these connections, find these additional use cases for the primitives, then we find more people who are interested in getting these features standardized and working to. Now, I said a little content author, the website owner, is only one target of our use cases. The next one is our website visitor. So I, as someone going to a website, have things that I want to do with a map that maybe the website owner didn't think about. So maybe the website owner didn't think about accessibility and the fact that I need to use my keyboard to tab through things, and I'd like to see what's currently focused. Maybe the website owner didn't think about the fact that I'm going to need to print out that map, or I'm going to need to export an address in a form that I can use in my GPS somehow. There are lots of use cases that are from that end user perspective that are separate from the desires or plans of the person who actually created the website. I'm not going to get too much detail here. We've actually got another talk later in the week. Nick Chan will be talking about her assessment for this report on some of the interaction patterns in the various web mapping tools and what that relates to the accessibility of the web maps for people who use the web in various ways. So moving on to our third category of use cases, that's your application developer. So this is, again, a website creator, but someone who's interested in maps in a more complicated level, interested in adding new features, because there is so much that could be done with maps on the web, and we're never going to have those all built into a standard tool. There are always going to be custom use cases in addition. So for the application developer who wants to build additional geospatial features, the use cases are about how much they can extend and build on the standard tool without having to recreate all the basic features from scratch. So one of our use case examples we've got is add a extra control that does something. So trying to keep it simple. So this was our contributor, Nick Fitzsimmons, who added this one. So this is the feature. It describes where the map is centered as we move. It shows a different latitude and longitude. And I can mark the current latitude and longitude at the center of it, and I can pan away, and then I hit another button and it returns back. So simple functionality, but actually there is a lot going on here. Updating when I pan the map, and it's changing the position of the marker, and then it's changing the position of the map on a different button, and it's responding to the button clicks as well as the movement of the map itself. And so we've got lots of different interaction patterns between what the user is doing, what the web map library code is doing, and then what the custom JavaScript is doing. And again, we've got this implemented in many different libraries with similar behavior, where we can mark the center, pan away, return back. And again, differing amounts of code depending on how well optimized the library is for these particular things we're trying to do. Although at this point, pretty much all of them, there's a lot of custom code because that's what we're doing. We're extending the map. So within all these use cases, as I said, there are a lot of little pieces that need to go together. So we're calling those the individual capabilities. So these are the low-level features that need to be available in order for you to build up the full use case. And within each of these capabilities, we're then looking at, is it implemented in existing tools? Is it implemented in a consistent way where we can say there is a clear pattern of implementation that this is how the standard should be designed because this is how users or developers expect it to be designed. We're looking at, are there any connections to existing web standards that could be reused in a pattern that's consistent with the web, or are there proposals that are for other web features that we could connect up? And are there use cases for this low-level feature that is use cases beyond maps? So I've already shown the example of wanting to be able to zoom in and adjust resolution on non-map content. More generally, just having pan and zoom, as it's a really complex interaction. There's different ways of panning and zooming depending on using mouse or keyboard gestures. And there are lots of stuff on the web that use pan and zoom, zooming in on a product photo on a store. That's not a map related, but there are similarities. And so if we had these low-level features, a sort of browser awareness of what pan and zoom is, it could be used in multiple places. The idea of having a pop-up tooltip, sort of, or an info box that pops up, that's something that happens in lots of user interfaces. But we don't have a built-in way to position things that are, pop this up next to some other anchored thing, but don't let it go off the edge of the screen, or don't let it obscure something else. That's, anybody who's done a website coded that by hand knows there's a lot of things you have to think about to get right. If there was a built-in primitive feature in the web for positioning a pop-up where the browser could do it once and do it right for every website instead of every website author having to write that code again, there are lots of use cases for that beyond mapping. But that said, there are lots of things that are needed for maps that are map specific. Maps need to understand latitude and longitude. They need to understand how that gets set to different projections and coordinate systems. And beyond this basic primitives within all the little parts that you need for a map, there is definitely, once you have those, there's a benefit of having the integrated feature, the very convenient declarative feature, so that the restaurant owner who just wants to put a map on their website with a pointer to the restaurant doesn't have to think of all the little parts that go into making that map. They can just say, here's the location, draw me the map. So that's a brief overview of the project. One thing that has been very clear working on this project is just how many detailed features there are once you start trying to list them all within the standard maps. So we are still working on the report. We are welcoming contributors to the report. It's all on GitHub, and we've got sort of issue discussion pages for every section of the report that are linked back from linked back from each section about, let's discuss what should we mention here, what should we conclude about, is this an essential feature of a web map, is this a nice to have feature of a web map, is this, okay, this is never going to happen in the browser feature. And we're going to have all of those, but we definitely welcome your contributions. And I've gone well over 15 minutes, so I'm going to wrap this up now and go back to my hosting duties.
Thanks,
Our
Amelia.
final talk of the day is by Dan Duck Little, who has been building maps on the web for many years, since 2004, when JavaScript was still new and wild. So Geomoose is built using XML, and Dan will be telling us about some of the lessons learned from that project, and take it away. Hopefully we can hear you.
Well, thank you. Am I getting through a little bit here?
All good.
Fantastic. So this is going to be a little bit different. I'm going to be covering something that's maybe a little bit more in the style of a retrospective on a project that's been around for a while, which is playing on the tune. Instead of HTML, we've used XML. I can be found all over the internet with the handle the Ducky Little. If anyone wants to have some follow-up conversation about Geomoose or any of the controversial things I may or may not end up saying today. A little bit of background on the project itself. It's actually an OSGeo project. Geomoose is a WebGIS client that started with a coworker and myself at the city of St. Paul in Minnesota in the US. The first release was back in 2004. And our big kind of coming out party was at the 2005 Map Server user group meeting. For folks who are maybe not into open source GIS software history, the Map Server user groups were the precursor to the FOSS4G conference. So this is how I start feeling old, knowing that we were presenting at conferences that were the precursor to FOSS4G. And we've done some cool stuff. Amelia mentioned that we use XML, and yes, we use XML and a healthy dose of JavaScript, as much of it as we've been able to squeak through the browser through the years. But to do some really cool things, such as describing pop-ups, providing detailed measure tools in the browser. That seems to be one of the next logical steps. As soon as you can put a map in it, can I measure it? And a lot of heavy support for OGC services through the years, including WFST support, so doing editing on the web, and also adopting sort of web-friendly technologies as they come through, such as the early GML, GeoJSON, and Mapbox vector tiles. But I'm going to put us in the Wayback Machine and talk about the web of 2003. It was a different place. There was a lot of things going on that were really innovative, but people were still trying to figure it out. For us as a GIS project, one of our big first goals was to talk to Map Server. So I mentioned that we come out of Minnesota, and folks may remember that Map Server used to be called Minnesota Map Server or the University of Minnesota Map Server. And my coworker, James Clausen, and I did actually work with Steve Lime on early Map Server code. And it was sort of the de facto standard for how you render a complex map for the web. And because it's 2003, we wanted to use all of the cool features of the latest and greatest browser at the time, IE 6. There might be a few of you on this call who are, kind of curse at on a regular basis the word Internet Explorer, but it was our best deploy platform at the time. Now, those two things were both pretty normal, actually. There are other people working in the space that really had those two goals in mind. What made Geomoose unique was that we were dealing with data for a large municipality that had multiple departments that were trying to inventory lots and lots of different assets. And that meant we had hundreds of different data layers that were being digitized and produced. So this was sort of Genesis. You'll notice that there isn't hundreds of layers here, but it deals with trying to describe different layers in a catalog. It has basic map controls. This was what a modern web application, including occasionally the broken images seen here, looked like circa 2003. But this is sort of what we started with. And one of our first keys was the fact that we could describe these layers and controls actually using XML. So we put all of this together and created an XML catalog, because really we looked at the various pieces that we had and that we needed to assemble. So map server is configured using a format called a map file. You can think of that as like a styling file for a shape file, because that's also what would have been popular circa 2003 to 07. And we had a lot of people contributing. So XML was really, really unique for us, and having a very basic markup was necessary for us because we needed to be able to describe, you know, how to organize all of these individual smaller pieces of work. So what Geomoose became was a really, really fancy XSLT. So that took the XML and translated to HTML, which then also had a giant JavaScript file next to it to render it. So I'm very sympathetic to the idea of we need to make the browser do more of this work. I really would have been sympathetic during this development time too. And because nothing's more fun than a code snippet, we can take a look at what this actually turned into. You can see that we described a map book. If you've ever looked at old school maps, particularly atlases, those were referred to frequently as a map book generically, because you had a book with multiple pages of different maps. So we created a map book XML format, and it had the ability to organize things hierarchically. So we called it the catalog, was part of the map book. Each layer got a label and a description to its source file and whether it was on or off. Could also be grouped because, again, we were dealing with hundreds of different layers. And this is what we got to from that Genesis moment to this. And you can see a lot of interesting components that are going on here. As the maps evolved, there was a lot of things that were necessary. We're also trying to convert people from using dedicated AutoCAD licenses for viewing maps. So if this looks more like a CAD application, then we achieved our goal at the time. But you can see in the catalog, many, many layers, very well organized. Rudimentary controls for navigation were available. And this entire user interface was described using XML. And then we made it pretty. One of the cool things that we were able to do is because at the time, the FDGC was offering grants that allowed for cross-community collaborations to share data. Well, having data defined as an XML format made it easy for us to interchange with other cities and counties. And so we were able to access some of that funding to develop the application some more and refine the XML format a bit more so that we could exchange these formats and the applications with different counties. At one point, nearly every county in Minnesota had a Geomoose website, and quite a few in North Dakota and other neighboring US states. In fact, we keep finding Geomoose installations all across the world because people were able to really dig into the idea that you could describe a map using XML. And whoa, it was good. Things were really fast to render. Even on, hardware that would have come with IE6 as the upgrade browser, it still ran really fast. And just like we were talking about HTML earlier being really great for editors and that sort of source-driven epiphany that you can have by looking at the site and looking at the source, we had that by being able to directly map the definition of the layer in XML to what they would see in the user interface. Some drawbacks to this. One of the big ones was that the order in the catalog, so how you define that XML structure, was how it was seen in the map. So if for some reason somebody put an aerial photography layer at the top of their catalog because they wanted users to see it, it would also end up being the layer that was at the top of their map, obscuring the entire view. There was also, because we had targeted map server and then evolved that to WMS, there wasn't really good ways of targeting different types of data sources. As much as you can come up with a way for defining how to describe that there's a data source there, the data sources are always going to be varied. And that's continued to grow through the web, even though there are standard ways of doing it. The other issue we had, and this was an implementation detail, is that every layer created an image tag. Really, really cool, because again, Ajax wasn't a thing. But then when we started doing tiled maps, it was making hundreds of requests in a second. So we started the next version of the project. Because Geomoose was built using a custom mapping library, we were sort of the 15th standard that XKCD refers to. Whereas, and the reason for that was because OpenLayers itself wasn't functional enough for us to switch over. But around 2007, it did. It also had much better cross-browser support because, well, in 07, you could still basically target IE and run everywhere. And we also worked with later versions of Netscape because they had the Venkman JavaScript debugger. But early versions of Firefox were coming out. They were getting really usable. JavaScript was becoming slightly less wild westy with the concept of classes and even user interface toolkits. But really, the main motivation was we needed to fix the relationship between a layer in the map and the definition of the map source. So we evolved the format. Here you can see it's a map book. We gave it a version of 2.0, and we define this code snippet here that is for, in this case, a layer of fire stations. It's saying that the type of this data is coming from map server. The name of the source is the map source. And this file element here is a shorthand to tell it, okay, this is the map file. So form the URL to work with that map file. And inside of that map file, there's a layer named fire stations. This allows you to do quite a few things. First of all, it allows you to group multiple layers into a single request because you can put 10 layers from a single WMS source in that layer. It also lets you break out, as an administrator, defining the catalog. You can have a difference between how those layers are stacked, where those rendered layers are getting data from, and how they're sorted in the hierarchy of your catalog. And this is a pretty basic Geomoose 2.0 application. You can still see there's many, many layers that it's processing all at the same time. It's providing that asynchronous layer stack here in the map, along with a number of controls. But not everything was great about it. In terms of technical implementation, we had issues with what was basically a custom Java compiler to put the different bits of JavaScript together. Certain components stopped working on newer versions of Internet Explorer. And a lot of JavaScript has moved to functional programming models, which there was no way we could support with what we were doing. But most importantly, the downside was because we had pushed all of the description into our mapbook XML format, it got unwieldily large. It was unsustainable to define every UI element inside of the XML. We inlined all of the code for styling data feedback, including pop-ups and identify templates. And so it was hard to keep moving it forward. It's hard to evolve the application because we sort of built ourselves into a tag corner in XML. Some other pretty important things happened while we were developing it. Google tiled the whole world about 10 different times and in about 10 different ways. People started putting mobile supercomputers in their hands. The OpenStreetMap project started, publishing new innovative ways of structuring some geodata, and a lot of vector data has gone to the web. You know, you think about the adaptation of GeoJSON or Mapbox vector tiles, and the way you, an administrator used to think about data was, I have shape files, I'm going to render them using my favorite map rendering service, and it's going to get put in the browser. But now you could just have data sitting in an S3 bucket somewhere, and I want to put that on my map. And that includes, you know, GeoJSON. It includes like Mapbox vector tiles. You could pre-render a whole region of vector tiles. And this even includes when you more streamable formats like cloud optimized geotiffs. What if I just have a picture I want to slice and dice and it's properly indexed? Or streamable JSON, things like new line delimited JSON that work with streamable web servers. I mean, cheap cloud compute means you can put terabytes of data on a map for pennies. So we thought we should adapt to the times. And that brought about the Geomoose 3.0 development. But even during our evaluation, even with all of the modern stuff that we were trying to adopt and looking at new patterns of programming, we still came back to the best way to describe some of this stuff is knowing that there's a map, that there are layers, and that there are map sources, and we can describe that in XML. So we can still use pretty familiar tags. So the new implementation was so fresh and so clean and looked almost exactly the same to a lot of users, because while we were able to develop a brand new application on a completely fresh stack, both to our administrators, who are our real target, and to the users, the application looked very, very the same. In fact, we were able to write a small conversion tool that allowed users of Geomoose 2 to uprate their XML to Geomoose 3. In fact, about 90% of the tags were able to migrate forward. This has helped a lot. We've got the ability to handle different types of data sources, be them raster or vector, or even things like GeoJSON and vector tiles. We can parse them natively and render them for users. We also created the idea of a query as concept, because sometimes you have browsers of different capabilities and you might want to present the data differently. For example, we have the ability to define a layer as being displayed in the map using a WMS source, but if you want to get the attributes for a feature, it'll use WFS. But we learned some stuff and some real important lessons here. Cartography is hard. Picking how you want to style those features once they're in the browser can be very, very difficult. And there's been a lot of successes and failures over the years. You know, map CSS, there's been, I think, 3 different flavors of that throughout the years. SLD, the OGC standard for how to define a layer, that gets pretty verbose and can be very scary for people, even with editors. Mapbox GL style sheets has been sort of a one organization show, though it's been pretty innovative. Open layer styling, as you could see in previous examples, just in the demo set, can get very complicated for simple things like a point. And map server map files are really great for styling stuff on the server, but there's no implementation in the client. And these are just the ones I could think of quickly that were mostly successes at one point. There's been a lot of other things that have bailed, that haven't quite made it through. The other thing we discovered is that performance can be quite hard. It's important to think about what happens when someone takes that really cheap available cloud compute power and tries to stuff it into your browser. Even with WebGL, you don't want to put gigabyte, you need to think about how you're going to put gigabytes of data onto your map. And communicating how to do the complex definitions can be hard as well. The query as thing that I was previously bragging about is also one of the hardest concepts to explain to our administrators who are trying to just get their data onto the web. Also, some future challenges just in the mapping sphere that I think we're trying to deal with as a project. We're trying to think about them. The first is 3D. that beyond how you define that data and how you communicate that data, point clouds are, as a technology, really, really evolving. There's a project called Entwine that puts 3D points into the map, and they've also become cheap and available because you can put a LiDAR puck on relatively inexpensive hardware and collect gigabytes worth of 3D points very, very quickly. Growing through mobile is also hard. People just expect a single site to work on just about every device that they have. No one wants to think about going to the /m.html site anymore. And a lot of maps cheat this by having an m.html site somewhere, or saying this doesn't work in your browser, but users are no longer accepting that. They want it to work on their tablet, their laptop, their 30-inch screen, and their 3.75-inch diagonal screen that they carry with them all the time. The other thing that's really ramping up that it's going to get harder to describe is with a lot of the new satellite data, Landsat, Planet, etc. There's a lot of accessibility towards detailed multiband data that are getting pushed to the browser. And that's going to be a future challenge for describing a map. So some big takeaways from the Geomoose project through the years. You can XML it. There is a way of describing maps where we can use XML and HTML tags to describe them and describe them effectively. We've got 15 years in the business at doing this. And so I think, and I think we do a good job. Also, I really think the idea of having a map source definition and a layer definition is very, very important. You'll hit a wall very quickly if there isn't some sort of definition between there. Styling is hard and gets complicated and needs to be considered hard. And yes, eventually a user will indeed try to stuff multiple gigabytes of data and render it in your browser. All right, I went kind of fast because it's hoping to get a lot of content in, but I'm always open to questions.
Thanks, Dan. That was really interesting.
Indeed, and a great starting session for the workshop to give that historical perspective of how much has changed and how much we still have to work on. The main form for questions that we're going to try and encourage people to use is the discourse at discourse.wicg.io. And that way people can ask questions even if they weren't here on the live session. They can follow up from watching the video. So unless anyone else has any logistics, I think we will wrap it up for the day. Remind everyone to check the agenda for the next session, which is a little over 30 hours from now. So either tomorrow or the next day, depending on what time zone you're starting in. And I will not be hosting that one. I think Peter Rushforth is up for hosting day 2. We'll be talking about the map data and server standards, OGC, and how those standards are good for the web or maybe not good enough for the web. And we'll also have a hopefully very interesting panel, representatives from government geospatial data providers on what web maps mean to their organizations. So I would like to thank everyone who has joined us today or who is watching after the fact.
I've posted links to the discourse forum with some topics, and as soon as Dan's presentation is available by video, I will post a link to that, but I'll post a link to his slides first. And with my appreciation, Dan, it's really interesting, and I would like to chat anytime offline.
Thanks, everyone.
Thank you. All right, well, see you tomorrow.
Right.
Thanks, everybody. Thanks, Ducky.
Thank you
Thanks.
very much, everyone.